Now we have to come up with a new convention in terms of distinguishing between both of those enantiomers. So the question is, well, how do we distinguish two stereoisomers that are enantiomers of one another? And so obviously we have to take a look at what's called the stereogenic carbon. And this is the carbon or carbons. We could have multiple carbons in a molecule um, that have four different substituents. So notice the key is that when we're talking about an sp3 hybridized carbon, that has to have four different substituents. So this eliminates any sp2 carbons or sp hybridized carbons. We're talking about stereogenic carbons are carbons that have four different substituents. And in general, you can have what's called a stereogenic atom, in which you can have any atom have four different substituents, be a stereogenic atom. And this doesn't happen very often, but it certainly can happen. So for example, nitrogen, if it's an ammonium salt, can have four different substituents located on it. But we're going to focus for the time being on carbon itself. So we first locate any stereogenic carbon or carbons, and then we are going to assign that carbon or carbons what's called an absolute configuration. The question then becomes, well, how do we assign an absolute configuration of, of that arrangement in space? Well, we have rules for that. And the rules are going to be based on the Kane-Ingold-Prellig rules that we used in assigning EZ nomenclature to alkenes. So we're going to do, the same approach. We're going to assign priorities to the four different substituents based on the CIP rules, the Kane-Ingold-Prellig priority rules, right? So make sure, again, you review those rules. They've come up with alkene nomenclature. They're certainly coming up again with stereogenic carbons. Then you place the lowest priority group behind the stereogenic carbon. And when you do so, if you're basically looking down the carbon substituent bond, right, between the carbon and the lowest priority substituent. And basically you can't see that substituent anymore, which means that the other three substituents should be facing you, right? So it's all about orientation. And when you get that correct orientation, the next thing you do is you connect the remaining three substituents with arrows. Now, how do you do this? Well, let's envision a Newman projection, right? So here I have a Newman projection, and I'm looking at my stereogenic carbon, and behind me is the lowest priority substituent, so I can't see it at all. And then in front of me, I have the three remaining substituents that I have prioritized. And let's say the priority is, the first priority is here, the second one here, and the third one here. So now I'm going to draw arrows to connect 1 to 2, 2 to 3, and then 3 back to 1. So I get 1 to 2, 2 to 3, and then 3 back to 1. The rotation of that, notice, is like a clock. Like if you're thinking about the face of a clock, we're rotating in a clockwise direction. When you get a clockwise rotation, you assign an absolute configuration of R. R is clockwise. Now, the opposite of that, again, looking down the stereogenic carbon where the lowest priority group is behind me, I can have this type of orientation where if I'm using arrows to connect 1 to 2, then 2 to 3, and then 3 back to 1, I see that the face of my clock is counterclockwise. And when I have this particular rotation, I assign the absolute configuration of S. So the term absolute configuration is based on the arrangement of the substituents around that stereogenic carbon. And therefore, it never changes. It's absolute. So there are a couple of things that you have to learn when assigning absolute configurations to stereogenic carbons. And the first thing is that you have to be able to recognize stereogenic carbons, right? And we've already seen, like I said, we've already seen some alkanes that contain stereogenic carbons. So for example, 3-methylhexane contains a stereogenic carbon. This is an alkane, and if you notice, what we're doing is we're trying to find a carbon that has 4 different substituents on it. There's one of them in this molecule, and it happens to be that carbon, right? That carbon has a methyl group, it has an ethyl group, it has a propyl group, and it has a hydrogen that's attached to it. So there's 4 different substituents attached to it, and therefore it makes it a stereogenic carbon. Now, I don't have to get very fancy to find a structure that has a stereogenic carbon. Here is 2-bromobutane. 2-bromobutane, if you notice, look closely, there is a stereogenic carbon. It shouldn't be too hard to find. It's right here. Right? That carbon has a methyl group, a bromine, an ethyl group, and it also has a hydrogen, 4 different substituents. And stereogenic carbons are found extensively in nature. So for example, here is a structure. This structure is of carvone. Carvone is an oil, and it has a stereogenic carbon. Can you see where it is? It's right here, right? So that carbon has 4 different substituents coming off of it. Yes, it's part of a ring, but notice that ring has no symmetry to it, and therefore going in one direction versus going in the other, the connectivity is different. And so I can assign priorities based on this CIP priority rules. And then of course it has this isopropenyl group coming off of it, and it also has a hydrogen coming off of it. And we're going to see later on how to assign that configuration, but I'll let you know right now, the R absolute configuration, the R isomer of carvone is the oil of spearmint, right? So everybody knows what spearmint tastes like. Everybody's chewed spearmint gum. The S stereoisomer of carvone is caraway seed oil. So caraway seed oil is the oil that, well, caraway seeds are often used in breads. And so it has that kind of a bready, yeasty taste to it. Notice the same structure, right? The same connection, just a different rearrangement in space gives you spearmint versus caraway seed. And I can draw, very large, even large structures. We see this is a particular stereoisomer that we call cholesterol. So cholesterol has, if you count all of them, there's 1, 2, 3, 4, 5, 6, 7, 8 chirality centers. And of all those 8 chirality centers, cholesterol has to have each one of them have a particular orientation in space in order for it to be cholesterol, which is pretty cool when you think about how nature constructs these particular molecules. So, recognizing stereogenic carbons, very important. Then, once you've recognized them, you can start assigning the priorities of the substituents coming off of them. So for example, I showed the 3-methylhexane. So here's 3-methylhexane. How do I assign priorities? Well, I have to remember there's a hydrogen coming off of it. And of course, that hydrogen gets the lowest priority possible because we assign it based on atomic number. And then I have 3 carbons attached. Again, remember, I then keep going until I get to a point of difference. And so the methyl would take the third lowest priority. The ethyl would take second lowest priority, and the propyl group would take the first priority. And that's how I would assign priorities. I can do the same thing with 2-bromobutane. Again, hydrogen's connected to it, so that hydrogen is the lowest priority. A methyl is the third, ethyl is the second, and bromine, which has the highest atomic number, is going to get the first priority, right? Here's an example. I have all sorts of things coming off of ethane, right? I have an alcohol, a thiol, a selenol. SEH is a selenol. And so I have a stereogenic carbon. Sometimes you'll hear the term a chiral center or a chirality carbon. There's all different types of names for these, but here we're going to choose to use a stereogenic carbon. But every once in a while I might say a chirality center. And again, trying to figure out the priority, we're going to base it on atomic number. So Se takes number 1, the sulfur is number 2, the oxygen's number 3, and lastly is the methyl group number 4. So I point this one out to show you that not always is a hydrogen going to be the lowest priority group. You may have a situation where you have an R group being the lowest priority group, and you have to keep that in mind. So now the last thing, we've now assigned priorities, and now we have to assign absolute configurations. But notice in the drawings above, there's really no way I can assign the absolute configuration unless I know the 3-dimensional shape of it. And therefore, the only way you can assign absolute configuration is if the carbon is drawn with the tetrahedral geometry. So, for example, I'll go back to the example of 3-methylhexane. 3-methylhexane, the way it's drawn, I can't distinguish between one stereoisomer or another stereoisomer. I have to show the tetrahedral shape. So I'm going to construct one of the stereoisomers. And notice there's another one, but this is one particular stereoisomer of 3-methylhexane, right? Where you have the methyl coming off of a carbon, an ethyl coming off of a carbon, the propyl coming off, and then the hydrogen. So we have the 4 substituents. And now what am I going to do? Well, I label them basically based on my priority assignments. So the hydrogen's 4, the methyl's 3, the ethyl's 2, and the propyl is 1. Now in this particular case, the hydrogen is already behind me. And therefore, do I have to draw a Newman projection? Certainly I don't have to. I can really just ignore where the hydrogen is. So I'm looking at 1, the propyl, to the 2, the ethyl, to the 3, the methyl, and so it looks like this. I'm rotating in a counterclockwise fashion, and therefore this is the S stereoisomer of 3-methylhexane, right? And so we would name it S3-methylhexane. Now, oftentimes when we're drawing stereogenic carbons, we tend not to, explicitly draw this tetrahedral shape. We can draw the bond line formula of it and simply show that, show the longest chain and then have one of them so for example, the methyl group coming out at me, and then the hydrogen would be going behind me, right? So remember when we talked about, how do you draw that 3-dimensional image as a bond line formula? It's really fairly easy to do. Again, I've randomly drawn a particular stereoisomer, and if I think about assigning, I get the hydrogen's number 4, the propyl's 1, the ethyl's 2, the methyl's 3. Again, in this particular case, the hydrogen is going behind me, so I can simply ignore it. Notice I get 1 to 2, 2 to 3, 3 back to 1. I'm rotating in a counterclockwise again. So this is still the S absolute configuration. This is still S3-methyl hexane. Notice if I switch the one of the or two of the substituents, I would get the R configuration. So this is one particular stereoisomer, and of course its enantiomer is the R isomer. Okay, so let's look at a couple of examples. Here I have let's see, this 1, 2, 3, 4, 5 carbons, so this is 2-pentanol. 2-pentanol. Now, when I assign priorities, the oxygen gets priority number 1, the propyl group gets priority number 2, and the methyl group gets priority number 3. Where is the fourth one? Again, it's hydrogen, right? And the hydrogen's going behind me, so I can, in this particular case, ignore it. So I assign priority 1, 2, 3. Notice I'm rotating from 1 to 2 to 3 and then back to 1 again. So my rotation is clockwise, and therefore this becomes R2-pentanol. R2-pentanol, and that's how we write it. So in parentheses R hyphen 2-pentanol. Here's another example in which now the hydrogen is coming out at me, and I'm explicitly showing that hydrogen. I don't have to. That hydrogen could be missing, and I could simply show chlorine as a dash. And of course, the hydrogen would be implied that it is a wedge. So that's something that we have to kind of get used to. So again, assigning priorities, the hydrogen gets 4, chlorine's going to get 1, it has the highest atomic number, and then the propyl group gets 2, and then the methyl group gets 3. Now, when the lowest priority substituent is directed toward you, you have to think about reorienting the molecule. Now, you could certainly redraw the whole thing, or you can cheat just a little bit. So remember, we're looking at these substituents like we're looking at a clock. And if you've ever looked at the back of a clock, you see that the hands don't move clockwise, right? If you take a look at the back of a clock, the second hand is actually, instead of moving clockwise, it looks like it's moving counterclockwise. So this is exactly like you're looking at the back of a clock. And if we realize that, then we can see what orientation we're going and simply reverse it. So in this particular case, we're going from 1 to 2, 2 to 3, 3 back to 1. I'm going in a counterclockwise fashion, but I'm looking from behind the face of the clock, right? And therefore, if I was looking at the front of the clock, the rotation would be clockwise from the front. And therefore, clockwise rotation is R, and this becomes R2-chloropentane. R2-chloropentane. So that's another type of orientation you may see in terms of that lowest priority substituent. It could either be going behind you, that's an easy case. It could be coming out at you, and you simply have to reverse orientation. Or it could be in the plane of the board. So let's look at an example here where we have 2-bromo, 2-chloropentane. And notice when we assign priorities, what is the lowest priority? Well, in assigning priorities, bromine's 1, chlorine's 2, the propyl group is 3, and now I have a methyl group that is 4. So here is a scenario where the lowest substituent is not a hydrogen. How do we assign priorities, right, when you have the lowest priority in the plane? Well, in this particular circumstance, whenever the lowest priority substituent is in the plane, the best way to do it is that you really have to think about the Newman projection and the placement of the atoms. So what we're going to do is we have to recognize that we're looking down that stereogenic carbon and in the direction where the lowest priority substituent is going to be behind that stereogenic carbon, right? So this is, in this particular example, this is the direction that we're going to be looking down. And when we do that, we can draw our Newman projection in which, the circle would be the lowest priority. So now what do we have? Where are the substituents? Well, the bromine is going to be on my right-hand side, pointing up. The chlorine's on my left-hand side, pointing up. And then the propyl substituent, C3H7, is pointing down. And now when I assign them, I see that, bromine to chlorine, chlorine to the propyl, and then back to the bromine. And I'm rotating in a counterclockwise fashion. And therefore, this would be S 2-bromo 2-chloro-pentane. So, the key is to recognize obviously how to assign priorities, but also to think about where your lowest priority substituent is. If it's going behind the plane of the board, you can simply ignore it. If it's coming out at you, you have to reverse the direction. If it's in the plane of the board, though, that's probably sometimes the toughest scenario, and you really have to think about the Newman projection to do so.